So first of all, my name is Jeroen Domburg. I am from Espressif Systems, and I'm a senior software / technical marketing manager. At least those are my titles. In practice, I am kind of sort of between the hardware and software side of things. Like I do software stuff, I also influence the hardware people. So I work at Espressif. We are a fabless chip company, as so many here. We are working on IoT silicon, specifically the end silicon that goes into devices that connects to things. We are headquartered in Shanghai, but we have offices all over the world, China, India, Czech, Singapore. Aside from that, we also have a bunch of people who work remotely, either from their home or whatever. So we're pretty spread around the world. So I'm going to start out by a little bit of a history of Espressif to lead in why we released this RISC-V chip. So and these are the chips we are at the moment well known for. That's the ESP8266, the ESP32, and the ESP32-S2. So this is in chronological order. So a long time ago, I think it's 7 years or something now, we started with the ESP8266 as our first chip. So you can see it here on a little module. These are the specs. So it's a 80 or 160 megahertz extensa core. It has Wi-Fi, that was its claim to fame. And actually, the most important part there was that we managed to create an IoT chip that used very few external components. So while other chips around that time needed like external magnetics and lots of resistors and capacitors, etc., that all ran at RF speed, so it was kind of hard to design for. We integrated so much on our chip that you only needed 5 external components in order to make a proper Wi-Fi speaking solution. So the rest of the specs was that it had about 190-ish K of usable RAM. It used external flash, as you saw in the previous picture. There's an external flash chip next to the chip. And it had a few peripherals, UART, SPI, GPIO, I2S, and ADC. And the main intent was that it was a Wi-Fi coprocessor. So you would have a larger application processor that used the Wi-Fi coprocessor to do its actual communication with the outside world. But it was also possible to run simple applications on the processor itself. So after that, we figured out that we might also integrate the application processor in the chip itself, and the ESP32 was born. So the ESP32 is a lot more powerful. Not only can it also run at 240 megahertz, it actually has 2 extensor cores. So it is a symmetrical multiprocessing core. So you can just start up threads and the operating system will decide on which core they run and it'll even out nicely. We also added Bluetooth and Bluetooth low energy into the mix. We gave it a lot more RAM, 520K. It still used external flash, which is really useful because if you run out of flash, you can just solder a bigger flash chip in and that's it. And it has a lot more peripherals. So after that, as a curioso, we also created the ESP32-S2, which is a lower cost version of the ESP32, kind of sort of. It's positioned in the market as such. It has the same extensor processor, but it only has one. It scrapped the Bluetooth functionality, has a little bit less RAM because it doesn't need to support Bluetooth. We added USB, and one of the interesting things here is that we actually dipped our toes in the water for the first time in RISC-V because we gave it a RISC-V-based ultra-low power coprocessor. So effectively what you can do is you can shut down the entirety of the chip, but you can still have a little coprocessor running that does things like read out sensors and see if it needs to wake up the main chip. And that chip in the ESP32-S2 actually is RISC-V. So just as an indication on the software side, how does developing for our chips work? Well, we have ESP IDF as our main development environment. It's based around FreeRTOS, LWIP as a stack, and we use CMake to tie everything together. We also include a lot of libraries to make it easy to talk to things you would find on the internet or the peripherals, etc. So we've got web servers in there. We've got an MQTT client in there. You can talk to all sorts of things. That's all integrated. So we also have support for other operating systems in the works. Notably, Zephyr and Nutix are starting to get traction to run stuff on our chips. On the software side, we're trying to be as open source as possible. So our SDK is fully open source, Apache 2.0. We also put it on GitHub. You can look through the sources. You can start issues if you think that something doesn't make sense. We accept merge requests, all that good stuff. So we have a technical reference manual that documents the hardware on a register on a register level. So in theory, if the drivers in the SDK aren't enough for you, you can use that to write your own drivers, or if you need to debug something, you can use that to figure out what's going on. There's only one exception there, and that is that the lower radio layers of Wi-Fi and Bluetooth unfortunately can't be open. That has a whole bunch of reasons that I'm not going to go into right now. Okay, the CPUs we used in these chips are Xtensa chips. So the ESP8266 uses the LX106, the ESP32 uses a dual-core LX7, and the 32S2 uses a single-core LX7. And those are Xtensa architecture CPUs. So what is an Xtensa CPU? You've probably heard of ARM, you've probably heard of MIPS, you've probably heard of, well, you obviously have heard of RISC-V as an ISA, but Xtensa might be a little bit less well known. So Xtensa is developed by a company called Tensilica, which is now part of Cadence. It's a 32-bit RISC architecture. There's some weirdness. Like it's not a super straightforward RISC processor, like for instance RISC-V is. It has a windowed register file, which can lead to some complications. And the reason why it's called Xtensa is that it's extendable. So Tensilica has this nice system where they want to make it very easy to add custom CPU instructions into a core. And that actually has support tools from, now Cadence. And the idea is actually that if you have a certain application processor that needs to run one single algorithm, you can actually simulate that algorithm, and the software will figure out which bits of the algorithm it makes most sense for to be accelerated in hardware. And it'll extend the core that you use in order to make specifically those algorithms faster. And they have pretty nice tools for that, as far as I understand. So yeah, that's really great. On one hand, it's a great processor. Like the CPU optimization bit that I just called is probably very useful for application processors. Furthermore, the IP is pretty well used. You don't often hear of it because it's used in application processors so much, but there might be an Xtensa in your CPU or GPU or your monitor or stuff. It's really used for embedded applications like that are deep within a chip. So that also means that it's pretty low on bugs, which is nice. Obviously, support tools for Cadence, you can get that. And at least within Espressif, our digital team has had almost a decade of experience with Xtensa, so they understand it pretty well by now. So unfortunately, Xtensa also has a few bits that are specifically for Espressif as a company with the culture that we have and that we want to nurture that are not so great. So first of all, application algorithm-specific optimization is pretty nice, but what we want to do is we want to have an open processor. We want everyone to be able to just write their own programs on this core. And so we can't hard code optimizations for one specific applications in our chip. So we can't really use that fancy stuff they have. The ISA is closed, as in the official documentation for the ISA are unfortunately not out there legally to be looked at. There is a GCC out there is a bin utils out there. You can derive the ISA from that, but in general, it's not as open as it could be. So yeah, the documentation for the ISA and other things needs you to sign an NDA, not with us, but with Cadence. And the tools that Cadence has are also closed source. So, okay, with that said, somewhere around 2020, we wanted to build a new chip. And this new chip had to have Wi-Fi and Bluetooth low energy. It needed to be cheap and cheerful. It was kind of sort of meant for, you know, Wi-Fi light bulbs where you could use BTLE to provision them into your Wi-Fi network, something like that. So it didn't need to be very high power, and obviously a light bulb is very price sensitive, so cheapness would be nice. So it didn't really make sense to make it multi-core, so single core would be good enough. And you know, it needed to have some other things. There needed to be some GPIO, there needed to be some RAM, etc. So we decided that we might want to switch to RISC-V for a main core for this. So we acquired a core. Our core is in order 4-stage. It is RISC-V, 32 bits with the IMC extension. So it's a full register file processor. It has a hardware multiplier and division unit, and it can run compressed code. We run it at 160 megahertz because that's fast enough. And the nice thing is for this core, we have the RTL, so we can actually modify it and find bugs and fix that ourselves. So, well, that's pretty easy, right? You take an existing design, say, for instance, an ESP32, you tweak the peripherals, like we don't need a bunch of things for a chip that's as small as this. And then you take out the extensa, and then you put in the RISC-V processor, and hey, we have a new chip. Okay, awesome, that's it, thank you for listening. No, obviously it wasn't as simple as that. Here are a few issues that we ran into. So the Extensa LX7 processor, one of the things it has is a debug unit and an interrupt unit that are integrated into the processor. So the debug unit can be connected to a JTAG port like directly, and the interrupt unit they have accepts, I think, 32 interrupts. Some of them are reserved, but those are details. So we externally have a mux there because in our SoC there are way more interrupt sources. So we externally have a mux that that allows us to select 32-ish interrupt sources from those 244. But the interrupt controller itself is internal to the Extensa processor. Furthermore, it has an instruction bus and a data bus, but Extensa is a bit weird in that they assume that those two buses point to separate address spaces. So RISC-V is a bit different. The core we had at least did not integrate a debug or an interrupt unit. And obviously the instruction bus and data buses will know they can point to the same memory. But with a digital team that is so used to Extensa that it took some time explaining that that was actually okay. So this means that we had to build a debug unit and an interrupt unit. And we took two different paths for this. For the interrupt controller, we actually tried to effectively replicate what we had for the Extensa. So it's effectively an adapter between the interface that the CPU used and the interrupt source multiplexer. So it does implement some things that come from the Extensa side. So there's priorities, you can select level or edge interrupts, etc. But unfortunately, it's not compatible with any of the standard RISC-V interrupt systems. So the debug subsystem, on the other hand, we managed to design entirely from scratch because we didn't have it only needs to connect to JTAG, not something more complicated. So we designed this from scratch, and we have a design that accesses that allows you to access all hearts. Well, we only have one, plus a system bus via JTAG, and this thing is all RISC-V debug spec compatible. So that is nice. The rest of the SoC, well, you see the block diagram here. I'll go through it really quickly because I don't think I have too much time left. So there's the RISC-V processor. We have some ROM, some SRAM. There's obviously Wi-Fi plus Bluetooth LE. There are a bunch of peripherals. One of them is a USB serial to JTAG converter, which is pretty nice. We have all the cryptographic stuff that you need to go on the internet safely. Yeah. So this is the chip itself. This is one of our early development boards. You can actually see the module with the chip on it, and the module is effectively all you need in order to go on the internet, so to say, to design an IoT thing that just does Wi-Fi and BTLE. Actually, we can make the module even a little bit smaller because we have variants of the ESP32-C3 that integrate the flash into the package. So you get a really tiny module there. The rest is just your standard development board. There's an LDO on there, there's a USB to serial converter on there that we might leave out on the next iterations. There's an LED in there because obviously you need to be able to blink an LED for a microcontroller system to prove itself. On the software side, we still use ESP IDF. We actually managed to integrate multiple ISA support into our SDK. And the end result is actually that you can use the exact same procedure and there's even source level compatibility between all the chips on the ESP32 line. We have Arduino support already in the latest beta, I think. We are already working on NATEC support, which is getting pretty far along. And obviously it's a RISC-V processor. It's like whatever the community decides to port to our CPU will probably work. So as tools, we use the standard RISC-V GCC. We also are able to use LLVM right now, which opens up a whole bunch of possibilities with, for instance, running Rust on this chip. We actually have TinyCC. Some of our maker fans is actually working on a nice solution where the ESP32-C3 serves a web page to a browser that is effectively an entire ISA where you can write your C code. It includes the TinyCC compiler in JavaScript that allows you to compile it to machine code that then sends it back to the ESP32-C3 and then executes it, which makes for a really nice low-level rapid development environment. But that's still work in progress. I hope he will release it eventually, but yeah. And also we have OpenOCD as our de facto open source debugging interface. So a little bit more on that, because the ESP32-C3 is fairly small and doesn't have that many GPIO pins. Obviously, you don't really want to spare like 4 for JTAG plus maybe 2 for serial port. So what we actually did was we integrated the JTAG adapter and the USB to serial thing in the chip. So if you want to debug this, you should be able to just directly connect a USB connector to it, and that will give you a USB to serial and a USB to JTAG port. And you can both upload new programs as well as debug the chip using only those 2 wires. Okay, so the RISC-V core already gave us a few advantages. Obviously, this is a bit muddy because it's an entire new chip design, so yeah, there's more going on there. But our friends at Hackaday did a quick comparison with regards to the amount of core marks we get in comparison to other chips. And you can actually see, if you look at, for instance, the green bits of the bar graph, that the T3 is a good, 20% ahead of the others. The only thing that's faster is the ESP32, either when it's clocked at 240 megahertz or when it uses both cores. So the ESP32 still is our powerhouse when it comes to processing power at this point. So the efficiency is a similar story. ESP32-C3 does a little bit better than the rest of the chips. Only the ESP32 can have a higher efficiency rating purely because there's more CPUs in there. So obviously, this is not the final chip with RISC-V cores that we're going to build. We have some internal roadmaps, and it comes down to, first of all, we want to have more compliancy. The interrupt controller we have right now, even though it functions well, is not compatible with any RISC-V specs. So we will likely take a PLIC or a click and add that to future designs. We can tweak the current core we have a little bit better, so we want to design a faster core that is more energy efficient. And we want to dip our toes into instruction extensions. We already did some of them on Extensa because things like artificial intelligence can have specific instructions for them that can accelerate them. We are starting an effort to port those to RISC-V as well. And finally, we want to have multi-core chips. We have the software experience with the ESP32 to make multi-core chips pretty user-friendly. So we want to translate that to RISC-V chips as well. So finally, if you want to buy one of our chips, you actually can't at the moment, but we should be good with mass manufacturing in a few weeks, and they should become available on Mouser and all the standard outlets by then. So if you want to experiment with a Wi-Fi RISC-V chip, then I would say take the ESP32-C3 into account. Obviously, I'm biased, but I do really like the chip. So that's the end of my presentation. Thanks for listening. I'm not sure if we still have any time for questions.
Trouble, and now it's okay too. Oh yeah. Okay. So thank you for a good presentation for the complete chip development, I think. And a few questions from audience. First one is, one of the strengths of RISC-V core is that they have RTL. Oh, is this? Yeah. What is the comment? One of the strengths of RISC-V core is that they have RTL. Yeah, it's maybe comment. And a question next. Is there any roadmap plan to develop next RISC-V device which has embedded Linux capable processor?
Sorry, I didn't quite get that question. You were breaking up. If you can copy paste that to chat, I can probably answer it.
Oh, yeah. This is a question about roadmap plan.
Do you plan to develop a Linux capable device? Thank you, Florian.
And yeah, which is Linux capable. Yeah.
We are investigating it. Let's put it like that. It is a bit of a. So the thing is that at the moment we have very, how do you say, with ESP IDF and real-time operating systems like that, we are able to make a very tight application. If we move to Linux-capable devices, it gets a bit more. So the issue is that the ecosystem is entirely different, as well as the CPUs get bigger, and you get into a different sort of ecosystem, so to say. We are still internally discussing if we want to go there. Let's put it like that. So unfortunately, I can't say anything conclusive about that.
Cool. Oh, okay. Thank you for answering the question. And that's all from the audience. So now it's the time to next. Sorry for quickly to moving to next. Thank you for your good presentation and good result of RISC-V course.
Yeah, thank you for having me.
devices.